Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. When combined with experimental work, molecular simulations can provide an impressive level of detail, generating insight that experiments alone often cannot achieve. Colloidal nanoparticles, typically comprised of an inorganic core surrounded by a monolayer of organic ligands, often have the organic component stripped using a pore solvent to make them suitable for a given application. New research using large-scale molecular dynamics simulations shows that the ligand stripping doesn't always increase with pore solvent concentration, challenging a widely held belief. The research involved iron oxide coated in oleylamine ligands. These form stable dispersions in hexane. Ethanol can be added to strip the ligands, and experimental work using thermogravimetric analysis and dynamic light scattering indicated different behaviours depending on the method of addition. Professor Joseph Tracy from NC State University explains.
If we slowly add the ethanol to the nanoparticles and hexanes, we strip more ligands than if we add the nanoparticles to ethanol, because then if we add the nanoparticles slowly to ethanol, then they're immediately seeing a very high ethanol concentration. So that would kind of be like dumping all of the ethanol in at once. And so in that case, where we would quickly introduce the ethanol, there's less ligand stripping because there's this protective effect of the particles agglomerate to some extent before the ligands are removed. So this agglomeration is a faster process, or at least part of it is a faster process. It's a matter that there's these processes, the ligand stripping and agglomeration going on in different time scales.
The nanoparticles began to agglomerate above 33% ethanol concentration, and this agglomeration inhibited ligand stripping. Simulations meant that this behaviour could be observed in detail and showed that the ligands began to digitate, preventing solvent molecules from accessing the surface of the nanoparticles. Larger nanoparticles, which have a greater ligand surface density, exhibited a greater degree of interdigitation, which enhanced the protective effect of agglomeration.
A lot of my research centers around Goldilocks rules, not too hot, not too cold. It was very interesting to see that we both agree experimentally and simulation that we have that instead of more solvent equals more stripping, we have the sweet spot. So it's very interesting to see that nonlinear behavior and then being able to explain it in details.
That was Professor Yaroslava Yingling from NC State University. The 33% threshold was initially observed in the simulations and then validated by experiment. Significant effort was required to develop a simulation that accurately predicted the experimental observation with a startling level of detail.
This dynamic ligands rearrangement being able to be replaced from the solvent stripped non-evenly, like one side is exposed and other one's not, right? Protected, like showing all of these dynamic qualities was not easy to get to. So we had to go back to the basis and develop new force field potential for the surface of a nanoparticle, new potentials between the ligands and the particles. So we can see all of this effect and still have a correct assumption on the solubilities and the rates and everything else.
The experimental systems were made small enough to be comparable to the simulations, which often featured just 8 nanoparticles in solution in a simulation box close to 20 nanometers across. Different solvents were also tested to try to understand whether there are equivalent rules for different solvents, and oleylamine was chosen as the ligand because it has neither a strong nor a weak binding affinity. Sitting in the middle means that extrapolation could be made in either direction. Now that the model is validated by experimental results, it could be used to model other systems, offering further insights into nanoparticle processing. These outcomes are made possible as a result of graduate students working closely together, as well as funding to support this kind of fundamental science. Professor Yingling and Professor Tracy both agree.
Excellent students who are driven and interested in going deep into the fundamental research, both experimental and simulation, because the grad students have to understand both systems.
We're grateful for the funding without which this work would not be possible. And we're grateful for the students without which this work would not be possible.
This work was published in a recent issue of Advanced Materials Interfaces. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.